Okay, let's get started. Hello, everyone. Good morning, good afternoon, good evening. Welcome back to the second year of SNAPP seminar. So we are restarting SNAPP seminar after a short break. Before we get started, I want to first take this time to thank the organizing committee from the previous year. So I want to thank Veena, Debankar, and Christina, who helped in kickstarting the SNAPP seminar last year, and then helped run it for a year and have now stepped down from the organizing committee. And I want to welcome the new organizing committee, which is composed of me, Jing Dong, Neil Walton, Yuan Zong, and Mariana. So the first speaker in the new SNAPP seminar series is Shipra Agrawal from Columbia University. Shipra is an associate professor of industrial engineering and operations research at Columbia. Her research spans several areas of optimization and machine learning, including bandits, online learning, and reinforcement learning. Shipra serves as an associate editor for several journals, including Management Science, Math of OR, Informs Journal on Optimization, and JMLR. Her research is supported by Google Faculty Research Award, Amazon Research Award, and NSF Career Award. Today, she's going to talk about dynamic pricing and learning under the BAS model. Before I hand over the floor to Shipra, just a couple of quick comments about how we run SNAPP seminar. So feel free to write, if you have any questions, feel free to write them on the chat box, and I'll keep monitoring the chat box and interrupt Shipra if need be. In addition, Shipra will pause 1 or 2 times during the talk when anybody can ask a question. And then we'll have a detailed question answer session at the very end. Thanks. Shipra, the floor is yours.
Thank you, Shiva. Yeah, thank you, first of all the organizers for inviting me for this very interesting seminar platform. And it's really an honor to kickstart the new year of this series. And the work I'm presenting today is based on joint work with my student Stephen Yin and colleague Asaf Zivi. So definitely want to thank them for their collaboration. So this work is actually appearing in ECE, which is running parallel to this seminar, not today, but on Thursday, my student will present it there. So if you are interested in learning more or asking him more questions, please feel free to join there on Thursday. And again, I want to thank all of you to be here while I know there are a lot of competing activities going on in parallel these days all the time. So let's get started. So this is our work on dynamic pricing and learning under the BAS model. So what I'm going to talk about today is a little overview. In this talk, our focus is on thinking about effects like social influence and imitation, which make the demand non-static over time. So why I want to emphasize that is, I know that many of you who are familiar with dynamic pricing and revenue management literature, it may not be a new thing for demand to be non-stationary, but in learning traditionally, mostly the models have been looking at either i.i.d. or independent across time or stationary distribution of demand or a stationary price response function. So that is more common, and I'll give you more literature overview later. So here we want to look at something like a BAS diffusion model, which is a very popular model, diffusion model for product adoption. And we want to think about how, if we have to learn this model while making pricing decisions, then what kind of challenges we face, and how is this different from the usual dynamic pricing and learning. And this, we'll see that in the talk, that this gives us a continuous time MDP, this problem, and the task is to learn a non-stationary optimal policy for this model while not knowing the model in advance. So just from the observations that we make based on the response to prices. So the main contribution of the work will be to give an algorithm, which is based on UCB type techniques. So these are techniques from bandit literature, but we apply them to this much more complex MDP setting. And we show algorithms with theoretical guarantees on how much worse they are. So regret is how much worse they are compared to the optimal policy for this model, optimal dynamic policy actually. And we also present, which in my opinion is actually the most interesting and the most insightful part of the result is that actually our bound is matched by a lower bound, and in this lower bound we'll see some interesting tension between the market size and the time horizon and the parameters of this problem. All right, so without further ado, then like here is a very general introduction to what I mean by dynamic pricing under uncertain demand. And I'm sure like people here are not new to this. Dynamic pricing is a very fundamental area of research in operations management, uh, made popular by airline and hotel revenue management, but more recently also has been looked at a lot in terms of online retail, and one of the and sponsored search ads and so on. And when we look at dynamic pricing and learning, there is the trade-off that we are very interested in is referred to in literature as exploration exploitation trade-off. So the idea here is that dynamic pricing originally serves the purpose of managing the trade-off between supply and demand, right? So you don't know, for example, if in airline how much demand you might have in future. You want to change prices to make sure that if you have more supply, the demand matches that over time. But when we consider learning, which means that we want to learn from the response to a price, we want to learn what the customer preferences are, then we see another trade-off, which is between learning and optimization. So we want to think about pricing in order to extract information about customer preferences, about how much they like the product, at what price they might be willing to buy it. So in order to do that, we want to dynamically change the prices and learn from that variation in demand. So this kind of trade-off has been looked at in dynamic pricing and learning literature, which is in no way new. There has been work in many different kind of models for dynamic pricing. So one of the most common model, which kind of started, which I think of as starting of bandit kind of work in dynamic pricing, is the independent stationary demand model, where every time you offer the price, the response is from the same stationary model in every time. But there might be some constraints on the supply and so on. So one of the initial work was by Kleinberg and Layton in 2003, and a lot of significant follow-up works, including Pespes and ZV 2009, and many others, which I'm not listing here because the list would be too long. But there is a very nice survey by Biden-Bohr in 2015, if you're interested. More recently, and this is again in no way complete list, I'm sure there have been a lot more papers more recently that I have not included. But what I want to point out is more recently people have looked at demand models and added context to it, which is a very important addition and in line with from multi-arm bandit to contextual bandit settings. So in context means that the price, again, the price response model is stationary, the demand model is stationary, but it takes as input the context, and that context may be non-stationary and it's oblivious to price, but it could be represent something like the season, the day, time of the day, whether there is a holiday going on that increases the attraction for certain kind of products and so on. So that context makes it really, takes it from a stationary, from a theoretically interesting model setting to a very practical interesting setting. There is also some work, much less compared to the earlier two categories I mentioned. There is some work on arbitrary non-stationary demand models, where the non-stationarity comes which is endogenous to the model. So there is some work on arbitrary, but non-stationarity, maybe endogenous, maybe exogenous, but it is in the work listed here, there is mostly bounded non-stationarity. So then you can produce some learning guarantees based on how big this bound or non-stationarity is. What is most related to our work is some structured models of non-stationary stationary demand, where there is a specific structure to why this is endogenous non-stationarity is coming into picture. And some of these models, including diffusion models, have been considered very recently in another paper. And the survey by Denver also mentioned some of them, although not with a lot of theoretical results, mostly empirical results. So let's come to the exact model that we are looking at, and what is the motivation behind looking at this model in this model or these kind of models with dynamic pricing and learning settings. So the effect that the model we are looking at aims to capture, in common parlance, we refer to them as word of mouth effects. So the idea is that there are two kinds of, we can categorize the influence, what affects the attraction of a product in two categories, external and internal. By external, we refer to anything that is extrogenous, that is oblivious to the past popularity of the product. So this can be think of effects that are into play even before the product is launched. So at the first time the product is launched, you're affected by the advertising that was done for the product quality, the brand, but not with the real experience with the product. The internal or social effects are related to the popularity of the product, the experience of other customers with the product, and the social influence that comes with that. So that is affected by how well the product has done in the past, by how do the other customers view it, and that might affect your attraction to the product. So this effect, the internal or the social effect, is one of the most important effects that gets ignored in the stationary models. So here, because of these effects, we see that that there is a non-linearity in how the demand grows for a product. In particular, often the more popular products get even more popular because of these social influences and imitation effects. So on the right, we have done like some very preliminary data crunching, and we can show that for using up some data from Amazon and Stack Overflow, that such non-linearity is present. So in the first plot on the top here, we show the new product reviews for Amazon. So we are using as the new reviews as a surrogate for new sales, because we don't have sales data from Amazon. So the idea is that the way reviews grow is proportional to the way sales grows, because presumably nobody who doesn't buy the product really wants to write the review for it. So you can see here that the new product reviews grow non-linearly with time, and they are not static, right? They have a very sharp curve to them. Same way here, we took another platform which is not online retail, but it has much more data, and it also has this kind of growth in product adoption in terms of number of answers that a question gets in Stack Overflow. And you can see again that the new answers is no way stationary. They have a life cycle to them, non-linear life cycle. And in fact, this kind of non-linear growth in demand and the effect of launch strategies and so on is well known by the sellers. And you see in practice a lot of strategies like giving initial discounts to boost initial adoption, sending products to highly rated reviewers and so on, so that it has a good launch. And that is done so that a product gets a good life cycle to begin with, and it can write the nicer curves over time. So BAS model is one model that captures this kind of, tries to capture at least this kind of influences on the product adoption. It's a very simple model, but arguably the simplicity makes it applicable to a wide variety of domains, at least in terms of capturing the general trend. It's not a very detailed model in the sense that it doesn't try to explain the behaviors, why this demand is growing this way, but tries to fit a general curve to the way demand grows, so that pricing can be made according to that curve. So the model basically has to define the scale of the market. There are two parameters, which is the market size and the time for which the product is being launched. And then the two important parameters of the model, which capture the external and internal influence, are coefficient of innovation and coefficient of imitation, alpha and beta. And why they are called this way, so I think of them as the alpha capturing the external effects or the static effects, and beta capturing the internal or popularity effects. To see that, let's look at the basic idea of the model. The idea is to think about the likelihood. So we have a linear model for how much likely a new customer is to buy the product, given that they have not already bought. Okay, so we think of that likelihood of buying a new product, given that they have not already bought, to be a linear function of the number of people who have already bought, the part of the market that has already bought. So alpha plus beta times FT is the equation that we put for this. And it's actually slightly easier for, in terms of analytics, to think of this as a differential equation. So in terms of differential equation, think of XT as the fraction of market captured at any time t. And the simple differential equation is that dxt by dt, the rate of new market capturing, is alpha plus beta xt. So alpha, so this part is not being affected by a fraction already captured, and this part is beta times the fraction already captured. So this times the proportion of the market not already captured, 1 minus xt. So this is the entire differential equation that's this governing xt, the fraction of market captured. So this is the growth equation. And the final, at the end of time horizon t, the market that will be captured obviously depends on alpha, beta, and t in this case. So note that there is no pricing yet here. So the original model it doesn't include the price, it just describes the growth. Assuming, for example, the price has been fixed in advance, so that might be captured inside alpha. So I'll just do this one more slide, and then we can, 2 more slides, and then I can take some questions. Let me know if there are any pressing questions, Shiva. So as I mentioned, the original model doesn't have any price, but there is actually a extension proposed even just a few years after the original model, which was by Robinson and Lakhani. And in this extension, a price effect is introduced in here. Effectively, the price is affecting both alpha and beta proportionally by this exponential function. And now once we introduce the price, we have a decision here that we can make it every time. So now the dynamic pricing problem can be described as this Markov decision process, but continuous time Markov decision process. So at every time instant t, in the interval 0 to t, we see the state, which is the fraction of the market captured so far. And we can decide, we can either decide to keep the price same as the previous instant, or we can change it at any instant. And depending on the current price, the change in the market captured, which means the new adoptions, is determined by this differential equation, and the reward is price times the new adoptions. The goal of the optimal pricing policy, optimal dynamic pricing policy, would be to maximize total revenue over this interval, which is given by the total price paid by the customers who adopted the product. Right? So this model, I have not introduced anything new yet. This is all known since 45 years basically. And this we know the pricing policy, it can be solved for analytically, and there's a specific form of this pricing policy that can be derived. And in fact, it's quite instructive and interesting to look at these pricing policies, especially coming from a stationary demand model, kind of where the price, like optimal price, is static. So if you look at this pricing policy, we can see that the price is non-stationary and state dependent. It changes with time and with the adoption level. And it also depends a lot on how beta and alpha and the time horizon are related. So if you look at the first top curve here, this is the case when beta is smaller than alpha. Think of the internal influence to be not that significant compared to the external one. So this is closer to a static stationary demand model. In that case, the price will decrease over time because, so the price should be static, but because there is like a resource here, which is the market size, which is decreasing, like the number of people who are still to buy are decreasing. Therefore, the price is decreasing over time. But if we flip it, meaning beta is larger than alpha, much larger than alpha, then suddenly the price curve changes. especially if the time horizon is small, then you want to actually start with low price. Make sure you attract a lot of customers initially by offering a low price. This is like initial discount, giving initial discounts. And once you have critical mass, then they help you popularize the product due to social influence and imitation effects. Then you can raise the price and extract more revenue over the remaining time. The curve again changes if you make the time much larger, because then you again reach a point at which the market is, you just want to get the remaining very small market as in any way possible. So then you again start decreasing price so that you can get the remaining market in the remaining time. So this was just to give you an idea of how different, especially if you have looked at other dynamic pricing and learning literature, where we are often targeting towards an optimal price. For example, the optimal static price for the deterministic equivalent of the problem. So we are often targeting that to learn that one single price there, but here we are targeting to learn an actual dynamic policy over time for this MDP and a non-stationary policy. So I will just finish defining the learning problem, and then we can take some questions. So the learning problem, so far all that I discussed was a deterministic continuous time MDP. Now, to get the learning problem, we will basically say that we don't know this MDP. So we don't know the model. We don't know alpha and beta of the model. We only observe the adoptions. So we only observe the state transitions, which is basically observing the number of new customers who are coming in, adopting the product. And we don't observe the adoptions directly. We observe noisy versions, which means that we observe a outcome of a Poisson point process whose rate is the same as given by that differential equation I introduced earlier. So we observe the random variables which are given by this Poisson point process with the rate given by Bass model. And again, the decision problem is same. We set the price, we observe the noisy version of the new customer adoptions given by the Poisson point process, and we get the reward, which is the number of new adoptions times the price that we set. And then we can choose to change price anytime we want. So this is our learning model, and the goal is again to maximize total revenue. And in the tradition of bandits or reinforcement learning, the idea would be to minimize regret. But the regret is not compared to any simpler set of optimals. It's actually compared to the optimal non-stationary stochastic dynamic policy. So it is the optimal policy for the stochastic model. And the main contribution of the work would be to show an algorithm with a upper bound on regret. And I'll explain these quantities, like how it depends on M and how it depends on T, and a matching lower bound. Okay, so I'll pause here and I can take some questions. I see some in chat, but I don't know if there are any pressing ones.
Yeah, I had a couple questions. So this is Alan. So M is known a priori?
Yes, that's a very good question. So we will assume that the market size and the time horizon is known.
Okay,
but we don't know the alpha and beta.
Good. And my other question, I think, may just be what someone asked in chat. Why is it important that there be noisy signals of adoption rather than you can just observe sales?
So think of this like the sales is a noisy version of the rate. So the rate is the expected rate. So it's not that I have observed noisy versions of the sales. It's more like the sales is a random variable with expected value given by this.
Okay. Thank you.
So I had a question. So this looks very interesting. So sort of the natural thought is it specific to the Bass model, or does it work for some more general class of models? And this power 2/3, right? Is it related to the number of parameters you're trying to estimate? Like, would it be 3/4 if there were three the three.
So I can give you like very brief answer to that, but we should discuss it at the end of the talk more carefully, because then we'll know what is specific to this and what's not. But I don't think it's specific. There are some things that we use about this. And yeah, this is like maybe my students next few years, that how to generalize it to other things, right? So we'll discuss that more. About m raised to 2 by 3, we'll discuss it more during the lower bound. But I believe it's not specific to number of parameters. It's more specific to the fact that the observation here is dependent. You can see my cursor, right?
Yeah.
Yeah, so the observation here, especially the popularity part, is being multiplied by how much popular it already is. So we'll discuss it more during the lower bound. So just hold on for a minute.
Thank you.
Hi, Shipra. I was wondering about the dependence on T in the regret, and T here somehow seems artificial.
Yes. So in fact, like we spent a lot of time on lower bound, and it was basically because of this interaction between M and T, which is very interesting in this problem. It's basically it's not. So if you want to get some intuition, think about like budgeted, if you have looked at budgeted learning problems, like where there is a bandit or a pricing problem with some budget constraint. And there, like, depending on how strong the budget constraint is versus time, you may see in regret dependence on budget or time. So if budget is so strong that, like, so small that time maybe doesn't matter, right? So it's something like that, but it's much more involved because there is no like such a hard stop like in the budgeted bandit problem. Is that a good intuition?
Or I was wondering, or maybe it's the number of adoptions that the amount of information you get somehow depends on the number of adoptions, and maybe
So it's like you can run for infinite time, but you only have like 10 customers who will come in. Then there's only so much information there, right?
Yeah.
You could just be waiting with a low price. So time doesn't really help because every time instant you don't get new information.
I actually have a follow-up question on the time horizon. So the BAS model itself has a natural time horizon. That is when like the whole market has adopted the product. Right? So here I should really think about, from a practical perspective, this is where I think about the shelf life of my product is, the capital T here, instead of like the time where everybody I would hope to reach have already adopted the model.
Yeah, so again, this will maybe when you see the form of the lower bound, it will become more clear. So again, interesting thing is the problem, it's related to what you're saying. The problem is actually interesting when time T is comparable to that time when so if I set capital T to be something like 1 over alpha plus beta, which is the time at which almost the entire market will get consumed. So that is the time where things become interesting. Right? If time is too larger than that or too smaller than that, then it's not interesting. You can just do anything and it will be basically the same. So even though we allow setting T to be anything, that's the region where things become interesting. So you can think of it that way, yeah. Right. Okay, if there are no more questions, I'll go ahead and we can come back to more questions after I present the results. So before I present the results, I want to present like one of the insights that was the most important for us to formulate both algorithm design and regret analysis. And this is in hindsight, this seems obvious, but it may be something that's unifying among other models that one may want to look at. So one of the things that we show is that the optimal stochastic dynamic policy for this model, the optimal value of that can actually be upper bounded by the deterministic optimal. You remember initially I started with discussing deterministic BAS model for which we know everything. Basically, we know the optimal policy before I introduce noise, right? So you can actually show that without noise BAS model, the optimal value of that model is actually upper bounding the corresponding stochastic optimal. And we show basically this by showing that, in fact, a stronger result showing that at every state, you can show that every state is the fraction of market adopted. The remaining value in the deterministic model upper bounds the remaining value in the stochastic model. So if I match the state, if I look at the two models, like in a coupled way, where they reach the same adoption level, then the remaining value actually is upper bound in the deterministic model, upper bound the stochastic model. And this is kind of counterintuitive just by looking at it, because it feels like the stochastic model has much more flexibility because it can see the noise and it can adapt prices according to that. But if you look at, again, if you go back to, any of you have seen budgeted bandits kind of, or resource constrained learning problems, we often use the result that the static problem with expected parameters upper bounds the stochastic problem. And we do that in the same way that we prove this, which is to show that the linear model, the linear optimization problem is actually concave. The outcome of that is concave in the budget constraint, the budget size. But here we have to show the concavity of this value function, which is much more tricky than showing those concavity of the linear programs. So this is one of the main results, and how it helps is it's two ways. First, because the deterministic model upper bounds the stochastic model, we get an algorithm design inside that actually, if we can estimate the parameters and we can imitate the deterministic policy, which we know, I showed you the form earlier for the deterministic opting policy, then that should be a good enough policy, assuming we have good estimation of the parameters. So we get a very simple algorithm design strategy. And the other thing we learn is that we can actually analyze this pseudo regret, and that which compares our revenue not to the optimal stochastic optimal policy, which we don't know anything about. Instead, we can compare it to optimal deterministic value, which we know a lot about, and that will upper bound the regret. In fact, we can show that this is not a very loose upper bound. The two differ only in order square root m, which is more than the order m raised to 2 by 3, the best regret bound possible for this problem. All right, so based on this insight, now the algorithm is actually quite simple, at least in terms of its formulation. So we do this kind of, you can think of it as explore then exploit kind of algorithm. So we basically offer an exploration price. This exploration price is a low enough price so that it's lower than optimal. You can even set it 0, but we don't want to say you have to set it 0, but think of it as 0 if you want. So offer a very low price until you see m raised to 2 by 3 customers. Or if you see the horizon has been reached. Okay. So when you see that many customers adopt the product, you stop and you estimate alpha. Okay. And you estimate a confidence region around, high probability confidence region around alpha. Now, after that, you proceed in epochs, and in every epochs, we re-estimate beta. So this is an important thing. So we only estimate alpha once in the beginning, but we have to be more careful about estimating beta. And so this is to point out that actually estimating beta is the more difficult part here. And why is that? Is because the BAS model, if you remember the equation, the observation of beta is through, so it's the effect of alpha and beta is through this equation, where beta is actually being multiplied by xt. So intuitively, what is happening is that beta is the popularity effect. You don't see the popularity effect until it is popular, right? Until there is a critical mass who has already adopted, only then you start seeing the effect of imitation. So estimating beta is difficult because you need to have xt large enough to see its effect. Whereas alpha, you see its effect from the beginning. So, but you cannot wait until xt is large enough to get a good beta, because you will lose a lot of revenue by then, or a lot of customers by then. So you want to basically re-estimate beta as xt becomes larger and larger to get better and better estimate of beta. So that's what we do. Basically, in doubling epochs, we re-estimate beta again and again, whereas we keep alpha estimate fixed. I mean, you can also re-estimate alpha for all that matters, but theoretically it's not required, because beta is estimation of beta is the bottleneck here. Okay. So after we estimate beta in a confidence region around beta, now we decide price every time given our current estimates of the confidence regions. we basically decide the price as a lower confidence bound, which means that we look at the uncertainty intervals of alpha and beta, and we choose the lowest possible price according, if you think of the entire, all the alpha and beta possible, and what is the optimal price for each of them at the current stage, and then choose the lowest one among them. Fortunately, it's not very hard to solve this problem. You can actually analytically compute you can write the expression for it. So don't think it's like a very complex continuous space problem that I'm solving. I can write the expression for it. Okay. So basically that's the algorithm. In doubling epochs, you re-estimate beta, you use the confidence intervals of alpha and beta to find the lower bound on the optimal price and offer that optimal price. So this is the high confidence lower bound on price that you are always offering. And for this particular algorithm, so I gave you like a rough expression for the regret. This is the complete expression. Only absolute constants are hiding here. No parameters are hiding in this expression. So it depends on, the main dependence is on M, which is 2 by 3. There is some dependence on the scale of the parameters, and there is dependence on logarithmic dependence on time. So as we already discussed, the dependence on time and market size is really interesting. In fact, one can show that the main interesting part is when time is some constant over alpha plus beta. In fact, you can derive this constant, it's like 2 times E. That's when the total adoption according to optimal pricing policy is M. Okay, it's full market. And that's where the problem becomes interesting. That's when the optimal deterministic value is roughly M log T. But if you make time much smaller than this, so if time is not constant and decreasing in M, then even the optimal policy only captures a sublinear market. So then this regret bound is not interesting. If you make it much larger T than this, then it's actually very easy to capture almost all the market using even very bad learning or pricing strategies. So again, then it's not very interesting problem. So the most interesting things happen around this time horizon, which is the time at which the market gets captured by the optimal policy. And this will become even more visible when we discuss the lower bound, because the lower bound will happen for this time horizon. The upper bound holds for all relations between alpha, beta, M, and T. All right, any questions before I'll just briefly discuss like the proof strategy. It's quite simple, especially if you have seen any banded proofs. But I'll take some questions at this point, yeah, if there are any.
Shipra, just a quick clarification question. So the revenue does not involve any discount, right? That's why when T is very large, you basically capture the whole market without worrying about the time.
Yes, that's correct. Yeah, that's an interesting point. Yeah, we don't look at discounts. I don't know, like if you put discounts, then there will probably be something interesting happening at discount when discount gamma is roughly 1 minus 1 over T or something.
I see.
So, but if it's a constant discount, then I don't know how the learning problem will shape. Yeah.
I see. And for the algorithm itself, how long should each of this epoch be?
Yeah, so this is, I just glossed over it. So the epochs is defined not in terms of time, but in terms of customers. So when you see M raised to 2 by 3 more customer come in, so when the number of customers is 2 raised to I times M raised to 2 by 3. So this thing in front of it doubles. So this constant in front of it doubles every time times M raised to 2 by 3. So you wait for that many customers. You don't wait for any particular time.
I see. And for every epoch, I suppose to offer initially this very low P naught price.
Yeah. So this is, yeah, I know this is not ideal. I think one can learn even with this, but yeah, that's something algorithm design would be nicer if a different price was not required. but theoretically, that didn't make much difference. So we did it this way. It's simpler to analyze this way.
I had a follow-up to my earlier question and your answer to that, which is, so you said for alpha you don't need m to the 2/3. Was that what you said?
For alpha, if you had to learn only alpha, so let's say beta is 0.
Yeah,
then probably you don't need m to the 2/3. Yeah, you'll have to change we won't have this algorithm then. Yeah.
I see. So you think it might be m to the half then, or?
Yeah, it's possible. Yeah, I think so.
Thanks.
Yeah, the lower bound you will see doesn't apply if beta is 0. Or if beta is known, let's say. Right. So if there are more questions, let me go ahead. So just to give you a brief insight on the upper bound, let me check the time. Yeah, okay. So to give a brief insight on the upper bound, the idea is pretty simple because the algorithm is really just about collecting some information, getting standard estimates from it. But main key aspect of the algorithm are two things. One, we improve the estimate of beta in doubling epochs, and two, that we offer a lower confidence bound on price. So that is the most important aspect, that we offer a lower price than optimal, right? So now we basically can summarize the analysis in 3 claims. The first that we saw already, that optimal, the stochastic optimal value can be upper bounded by deterministic optimal. And we also know that in every epoch, we offered a near optimal price for those alpha beta, right? So every time in every epoch, we estimated alpha and beta, and for our estimates, we are offering optimal price, whatever our estimates are, the lower confidence bound on the estimates. So what we can say is that the total number of adoptions over the entire time duration, we are getting at least as much as optimal deterministic will get, because we are offering lower price. We might be making less revenue because of lower price, but because of the lower price than optimal, we must be getting as many customers. Now there's some, like, this is not exactly accurate, because in the deterministic model, there was no noise, and we have noise. So pricing policy is better, but in terms of number of customers, but there is some noise. So except for that statistical noise, we are getting at least as much customers as optimal deterministic. We are not making as much money on those customers. So what we can say roughly is that if we look at the optimal deterministic value in every epoch for that many customers, for alpha beta versus our lower confidence estimates of alpha beta, then the difference between the two values is the total difference in the regret. So the optimal deterministic for our estimates versus the optimal deterministic for alpha beta. Okay. So now all we need to bound is, in some sense, this difference between the optimal values given the difference in the parameter estimates. So this is like a Lipschitz bound now, right? How much the optimal value in the deterministic model change if you change the parameters. And basically then the analysis is quite simple. You do an error bound on alpha and beta, and you multiply it with the number of customers on which those error bounds apply. And that's why doubling epoch is important. You make sure that higher error, so low error estimates are being applied to larger and larger number of customers. And that's how we get the upper bound on the regret. I want to save some time to discuss lower bound because it's also very conceptually interesting. Does anyone have any quick questions in between? Right, so I'll go ahead. So the lower bound, so here's the detailed version of the lower bound. I mentioned briefly that it's matching. So here's how it is matching, so to say. So what we show is that, so there is some assumptions that we have to make, and one of them is technical, I feel, and one of them is needed. So the first assumption we make is that price is bounded by log t, order log t, any constant times log t. So we kind of assume that the algorithm that we are proving lower boundary, so the lower bound will be any algorithm for this problem, but we have to say any algorithm which never offers a price greater than any constant times log t. And optimal price is actually bounded. And we feel this assumption is required. It's not technical. Like, we cannot allow for arbitrarily large prices. But we also feel that it's kind of standard for this kind of literature. In fact, like the other works that we compared to, which also consider BAS model, assumes a constant bound on price. So it's kind of perceivable that you cannot offer arbitrarily large prices in real setting. Because if you offer arbitrarily large pricing, it's very difficult to say how much time do you have to learn if you allow arbitrarily large prices. So we make this assumption. So any algorithm which offers bounded price and any algorithm that doesn't change price between customer arrivals. This, I believe, is a technical assumption, but we had to make it to make some stochastic processes nice. So we put these two restrictions on prices on algorithms. So algorithm can change price anytime, but not like after between like two customer arrivals. So it can change a price after it sees a new arrival, for example, while waiting for the other arrivals. So given any algorithm with these two restrictions, we can show that I can find like many markets with this regret lower bound. In particular, fix any alpha beta and time to be of this order, then there exists a market within some range of that beta where the algorithm's regret for that market will be at least m raised to 2 by 3 times this. Okay, so basically it's kind of saying there exists a market, but actually it's saying that it's not like that market only exists for some very particular alpha and beta. So such markets exist for almost all alpha and beta. Like if you give me any alpha beta, I'll find a market very close to it, such that for this kind of time horizon, any algorithm will give you this much regret. Okay. And this is for NEM. It's asymptotic in M. So the proof strategy starts very similar to any learning lower bound that you might have seen. So the first step is to show that there is some information theoretic lower bound on number of samples you need to learn beta, basically. So alpha is not the bottleneck here, as I mentioned. So basically we show that without seeing sufficient number of customers, in particular m raised to 2 by 3 customers, you cannot distinguish between two markets where beta differs by a constant. So if you have, before you see that many customers, you cannot distinguish between beta versus beta plus epsilon, which market these customers are coming from, you cannot say. And this is a standard KL divergence-based proof, which you might have seen in multi-arm bandits. The reason it's m raised to 2 by 3, if you do such a proof in multi-arm bandits, you get square root m. The reason you get m raised to 2 by 3 is because it's beta x, not beta. Okay. So if you did this proof for alpha, you will get square root m, this KL divergence-based proof. So from here, so this almost finishes the proof in multi-arm bandit, this step, because then you can say, oh, if the market differs by a constant, you will suffer, you cannot distinguish between whether to play arm 1 or 2, and you will suffer constant regret every time, something like that, right? Here, there's a story is a little bit more complicated. The question is, do we really need to distinguish beta by epsilon in order to be able to offer good prices? So we have to show that, in fact, when T is this critical T, then there is a difference between optimal prices for the two markets. The two markets' optimal prices do differ by a constant. Okay, so you do need to, in order to be within a constant of the optimal price, you do need to distinguish between the two markets. So now again, but we are still not done, because you could say, what if I don't offer optimal price at any given step? I could maybe make it up, like, because it's a dynamic pricing policy, how much the value differs for the two optimal prices, right? So in fact, you can show, the next step is to show that the value of optimal policy under the two prices which differ by, like if you don't offer optimal price but you differ by a constant, then the value, so this is the key expression, the value differs by the squared of the sum of the error in the prices. And this basically concludes the derivation. So the summary is basically we say that before seeing that many customers, you cannot distinguish between beta versus beta plus epsilon with a constant probability. The two markets' optimal prices differ by a constant. And if you have prices differ by a constant, the total revenue differs by a constant times m raised to 2 by 3. And that's how you get a lower bound. Again, like it's the actual proof is not 3 slides worth. It's much longer, but these are the main insights into the proof. Yeah. Before I summarize, if anyone has questions on the lower bound.
I had a question. So the proof, the outline you described sort of says that you want to first estimate beta and then find the price. Does your proof cover like some hypothetical policy which?
Yeah. No, the proof is not based on a particular type of algorithm. So if you look at this, right, this doesn't say about how we are doing this. This is the intuition, but the lemma is simply this. Just to distinguish, just to say that these observations came from this market versus that market. So with constant probability, the two sequence of observations could have come from any two markets.
Got it.
So this is just the intuition, the first part. The actual lemma just says that to distinguish between the samples from the two markets, you need that many arrivals.
Got it.
I have a question. Is there an intuition for why there is a 2/3 here when you have beta x?
Yeah, so the intuition is kind of this, that you so do you mean 2/3 versus something else? Or
yeah, 2/3 versus like why does the square root become 2/3 when you have an additional x?
Yeah, I don't have like intuition except the KL divergence way. So I think if you want to think about information theoretic reason, I think if you see the KL divergence argument, you will see it.
I see.
Because it's just that the KL divergence between the two sequences is just that way. Like it's yeah, I don't know how to give a more intuitive answer. Okay. But if you think of a reason that's beyond our estimation method, but something information theoretic, I would encourage you to see this part. Yeah.
Okay. Thanks.
Any other questions? Okay.
Sorry, quick clarification. So you have this m over epsilon power 2/3, right? Mm-hmm. What is epsilon? At the end of the day, you're going to pick epsilon to be some constant.
Yeah, constant. Okay. Yeah, that's not the case in banded proofs, but there are other kinds of banded proofs as well. But yeah, we'll pick it as a constant.
Okay. Thanks.
All right. So to summarize, we look at the pricing and learning problem under BAS model, and we basically show that it's basically a problem of learning a non-stationary optimal policy when you don't know the MDP. Luckily, we are not looking at the general MDP. We are a very specific structure, and that structure helps us in basically following the deterministic version of it, following that policy, and just use bandit techniques instead of like going full-blown reinforcement learning for this very complex MDP, right? And we are able to use simple techniques like lower confidence bound estimations to find the deterministic, to find the optimal policy, to mimic the deterministic optimal policy and compete with stochastic optimal. Okay, and one of the takeaways that for me for this work was this interesting trade-off, like interesting dynamics between time and alpha, beta, and m that we kind of understood through this work. And I hope this gives insight about other models which are related in terms of some interaction between market size and time and parameters of the problem. So as Yash mentioned briefly initially, I think there's a lot of interesting questions that this raises. In particular, What about more general models? Like, is there something specific about BAS model that we used? And if you go through the proof steps, you will see there are some things we are using. We use specific structure in terms of estimation of alpha beta, but I don't think that's so crucial. Like if you have some parametric model, you can still fit like a least square estimate. We do just simple like least square estimate kind of thing. You can do that for any model. The main property that we use, I feel, one is the concavity of the value function. We use that to show that optimal deterministic is better than optimal stochastic. And maybe that is easy to prove for other models as well. Maybe not, we don't know. There are other things which seems more artificial and not so crucial, but they could become important in the analysis. But it's an interesting question as to how much this can be extended. How can we like make a more higher level statement about which MDPs this can work on? And it's also interesting to see if other extensions like contextual versions of BAS model can be considered. I think that would be crucial for practical applicability of this. Like right now, it's theoretically interesting, but I don't think I could apply this convincingly even to like Stack Overflow or like Amazon, because you cannot learn a different model for every product in the catalog, right? You have to learn like a contextual version of the model that says how the demand will be depending on the product features and so on, right? So that's the summary. And as I said, the paper will be presented by my student on Thursday in EC at 1 p.m. session. And the title is same as this talk. Thank you.
Let's all thank Shipra. Okay, the floor is open for questions.
I have a follow-up question to an earlier question someone asked about the fact that you assume we know M exactly. So if in reality I know M, but with some error, how much would that affect the results you're presenting here?
Yeah, so that question we have looked at. It's interesting. Like I compare it similar to either not knowing time horizon in bandits, which has been handled, but even more crucial, like know whether you know budget in a budgeted bandit or not. So it's somewhere between that. It's not as crucial as knowing budget in budgeted bandit, but it's not as loose as not knowing time horizon in bandits. So it's somewhere between them, because you need to know the scale of the problem you're dealing with in some sense. It's harder to design algorithm without it. It's harder to plan without knowing like what your resource is, like your market size in some sense, your resource, right? So yeah, it's an interesting question to design like any time kind of algorithm, like any market size algorithm. Maybe you can estimate as you go. I don't know. Yeah.
Thank you. I have another question about the initial modeling assumption, actually. So you make the assumption that the underlying BAS model is a deterministic model, and then what you observe as the realized demand in each period is a Poisson based on that BAS model. But I guess you could also make the initial BAS model as you can add like a Gaussian noise or Brownian noise to it to make the model itself stochastic. Have you found the difference between the two modeling options, or there would be almost the same?
Yeah, so we actually thought about it a lot, and we spent actually more time than you can imagine on deciding the noise model. It seems like if you make it a Gaussian, the issue of the scale of the noise becomes very difficult to handle. Like, because with Poisson, the scale is determined by the expected value, right? So the standard deviation is itself determined by, there's only one parameter. In Gaussian, there's like two, mean and the variance. And the scale becomes very crucial. How you decide the scale completely changes the problem. Like if you make it a constant noise versus like you make noise dependent on the price, whether you make it dependent on the scale of the demand, and it makes it very too much control in the hands of the noise model, it seems like. So it seems Poisson is more natural. It has also been used, like we saw other papers, like empirical and otherwise, like theoretical using with past model, like Poisson kind of extensions. So we felt it was more natural.
Thank you.
Maybe I had one quick question. It's more about the model and something you said right at the beginning, which is that you might choose at the beginning when you launch a product to spend more money on advertising or to somehow reduce the price in order to, so I was wondering, to what extent is that accounted for in the model by initially choosing this P0 below the optimal price, or to what extent would the parameters alpha and beta be price dependent? Would that be an additional extension to the model that would be worth considering?
Yes, that's a very good question about the modeling. So if you look at this particular model, there are a lot of things that kind of already determined, right? So in a way, it's saying that when you choose a price, you're affecting both alpha and beta proportionally. I imagine like if you did something in the beginning, which is not price dependent, but something like some advertising, that would change alpha itself, right? And then proportionally, you're assuming if with this alpha, you offer a low price, you get much more attraction. So I imagine that doing some initial brand advertising or something affects alpha. That's the spirit, at least, of this model. But yeah, again, it's a model. So.
Yeah, I understood that from this when I asked the question. But I was just wondering if you were thinking of it that way. That
Yeah,
if I say
I think
this
of
is
this
to lose in order to get the product, going. If you see what I mean.
Yeah. At least the way I understand the spirit of this model is that anything you do before the launch or anything that is external to the process, like which is extraneous to the actual sales process, is captured by alpha. So I would put, if I were to make an context-based extension, I would put the context dependence on alpha.
Okay, great. Thank you.
I have a quick clarification question again. So can you go to slide 8? I think it's probably, okay. So in P star, on the right-hand side, there is X capital T star. Does that mean that P star depends on the future X?
Yeah. So that's a good catch. So this is the way the price expression is, but there's also an expression for XT star. So this is all calculable,
Okay.
but it's that expression is not very informative. It's kind of useful to look at it this way. Yeah.
I see.
XT star, like at the interesting range, is roughly M.
Okay.
Yeah.
Okay. Got it. Thanks. Okay. If there are no more questions, let's thank Shipra again.
Thank you.
We'll end the recording as well as the live stream now, but feel free to have any other informal discussion.
So Shipra, again, very interesting talk.
Thanks.
At the end, you had